Alright, so we're going to talk about a Michael addition. So an aldol type reaction with a Michael addition. Let's start off with two things. So first thing you look at, say there's a base in here. And since I'm doing this on the fly, I can't draw the product off the top of my head, so I'll just do this together. Normally we'd have the product drawn. I just can't do that right now off the top of my head. I'm not that good. So let's try this. So we have OH minus. We got to find the most acidic CH. So there's a couple alpha CHs here. There's a couple options. There's an alpha CH over here. There's an alpha CH here. There's an alpha CH here. There's even a alpha beta gamma CH here that could be acidic. We just got to pick the most acidic one. So which one's going to be the most acidic? The second one, because it's between the two ketones, right? So two things pulling on it, two chances for resonance either way. So let's use that. I'm just going to put the negative charge there. And of course we know that we could do resonance structures either way. So obviously that piece is going to be our nucleophile. Has a negative charge. So that means the other thing has to be our electrophile. And more often than not with these, if you see the opportunity for a beta addition, right? If this is alpha and beta, like a Michael addition, that'll happen. You'll do the Michael addition. Right? So negative charge attacks. Kick everything up. All right, balance my charge, all that good kind of stuff. Got that done. Now at this point, we also should, water was along for the ride here. So at this point in the past, you've seen it where there's been opportunities to do like a cyclization at this point. So let's see if that's possible in this example I gave. Right, 1, 2, 3, 4, 5, 6, right? But I don't usually start with this, so that should be 1, 2, 3, 4. Right, this carbon is the nucleophilic carbon of the enolate. Right, this is the enolate. That carbon right there is the nucleophilic one. So if it attacked, it'd be a 1, 2, 3, 4-membered ring. Probably not gonna happen, a 4-membered ring, right? So this one can just end where these electrons come down. Pi bond grabs the H. We've formed a new carbon-carbon bond, but nothing too cool has happened. Right? We just added to that piece. And the new H we added on, right, ended up right here. So let's go over, I called it a MetalX Exchange. And I showed it a couple different ways. Or I showed it in a couple different situations, but always the same mechanism. The book actually showed more than one mechanism for this, but I wanted to focus only on doing this with an SN2 mechanism. So two ways you've seen it. You've seen it where you have like a halogen on like a benzene ring or an sp2 hybridized carbon, right? An sp2 hybridized carbon. And let's say you have this, 1, 2, 3, 4. This N-butyl lithium, right? 1, 2, 3, 4, just normal lithium, straight chain. So the carbon's bonded to a lithium, that's really like an ionic bond. So it's like a negative charge there. And what can happen is these two electrons here attack the bromine, and the two electrons that the bromine is bonded to go right to that carbon. And now this carbon really has a negative charge, and the lithium is there. And we also made bromobutane. Right, so it's a lithium halogen exchange, a MetalX exchange. the metal exchanges for the bromine. And the mechanism right here is, what does this mechanism look like to you guys? What kind of mechanism is this? It's just an SN2. It's just an SN2 mechanism.
What makes the bromine electrophilic in the face?
Right. So why would the bromine be? So that's part of the. I mean, the bromine's big enough where it's polarizable, and there's other mechanisms for this that maybe would make more sense. You could do like an SRN1 for this, but I just like the SN2 style. Go ahead.
You couldn't do an SN2 on an SP2.
I can do an SN2 and an SP2 hybridized, but where is the SN2 taking place at? It's taking place on the bromine, essentially, right? And the bromine's still SP3 hybridized, right? So,
I don't know, like on a test, how would you?
so at this point, right? So we've turned an electrophile into a good nucleophile, right? But we don't have very much of this or this around. So normally we'd add in, right? Let's say we want to add in, we would add an electrophile. So let's say we add iodomethane, right? So we had a whole bunch of iodomethane. So then our nucleophile would attack that, and we make the ring now with a new CH3, and we'd have lithium iodide as well. This can attack this. There's just not very much of this around, so it's a matter of concentration, right? I would just add a lot of methyl iodide to make sure these two things reacted first. So that's the MetalX Exchange on an SP2. Right, this is on an SP2 hybridized thing. We can also do it on an SP3. And you've seen that. We saw that with, we kind of did it as a, I think we did it as a kind of a carbine example formation, right? If you took methyl lithium, right, it could attack the bromine, the 2 electrons that go there. All right, it's that classic carbene intermediate, a negative charge on a carbon with a good leaving group there. Go ahead and make that carbene. Right, but that's another way on SP3 hybridized how we could do that lithium halogen exchange, right? The metal halogen exchange, where the negative charge is over there, and really, right, the lithium is we draw it here, right? It's really like a carbon with a negative charge. It's like an ionic bond, right? But it takes a carbon that was delta plus and makes it delta minus or even a full minus. Right? So it changes it from electrophile to nucleophile. So then, yeah. So then at this point, you have this is a carbene now, right? So now you can do all the 4 carbene type reactions. I think in the homework I did like a random, like a CH insertion way across the ring, right, where the negative charge attached and went over. You can do CH insertions. You can do additions across pi bonds. Right, what was the other thing? You could do lone pair nucleophiles. What was the 4th one? 1-2 shifts or something?
Yeah.
1-2 shifts is the other one. So it's kind of touched on carbines, kind of take it a step further, just remember what carbines are. So carbines, we always draw them with a plus and a minus and then bond 2 other things, but what does it actually look like? Hybridization state is sp2 hybridized, which means it has a p orbital and 3 sp2s. And we draw with this plus minus for a reason, because part of the carbene is electrophilic, but also part of it's nucleophilic. So it can be drawn, right, with a p orbital, which is actually empty, but with an sp2 orbital that has 2 electrons in it. And then back here, it would have its regular, right, these are CC bonds, let's say, whatever these guys are, CH3s. So you can see, right, part of the carbene is an empty p orbital, so that's like a carbocation, right? But then there's another part of the carbene that's like a nucleophile. So that's hence the plus minus. You get both kind of characteristics of it, which is important for how it reacts to that plus minus part. Right, so it can react like a nucleophile here in this part and attack something like the minus charge does, but then it also has the empty p orbital where something can attack it as well. Okay, think of a C to O migration. So one I showed you guys in class was a Baeyer-Villiger, which I expect you to know, but I'm not going to show you that one now. What I'm going to show you, I'm going to go with I'm going to start with carboxylic acid. See if this works or not. We'll find out real fast if this is stupid or not. And we'll start off with OH minus and Br2. Be step one. So the first step should be pretty easy. Carboxylic acid and OH minus, what's going to happen? We're going to deprotonate, right, the carboxylic acid. So we make the O minus, and we have the Br2 in there. So what are we going to do with the O minus and Br2? Attack the bromine, right? Right. So we essentially did here, right? If we're talking about CO migration, in this case, this is not a Baeyer-Villiger. I want you to look up the Baeyer-Villiger. This is not the Baeyer-Villiger. Not the Baeyer-Villiger. We've put something on the oxygen. That's a pretty good leaving group, right? Br is a pretty good leaving group. Everybody can agree on that? Yes? So we also have Br minus. So let's just say Br minus, right, decides to attack the electrophilic carbon of the carbonyl. Kicks those electrons up. So now we have what? A tetrahedral intermediate, right? Looks kind of weird with this oxygen bond to bromine, but right, it's again, right, we've seen carbon bond to N2. Right, it's just putting a good leaving group on something, right? So if we want to migrate something, we have to have a good leaving group for something to leave off it. So here, tetrahedral. It's okay. I'll bring it back. Tetrahedral intermediate. O minus. Right? It's coming down. But now in this case, in the surprise of all surprises, the Br is not going to get kicked out. Right? Instead, this methyl is going to migrate and attack that oxygen. And as that happens, this oxygen-bromine bond is going to break. Now, if on the test, I would give you the products, right? So it's kind of hard for me to do that right now. But normally I would give you the products so you know where you're going. Right? So what happened? Let's we number our carbons, 1 and 2. So 2 is still bonded to what? Carbon 2 is double bonded to the oxygen. N to the bromine is still there. N to this other oxygen right here. This oxygen right here is now bonded, right? The bond between 1 and 2 broke. If this is 2, 1 is now on this oxygen. Right? And what else to balance my charge? What do I need left over? There should be a Br minus floating around as well. Now this is unlikely that this would happen, right? Normally, what I probably would have done was instead of having the Br attack, I'd have step 2 and have something else attack. But it doesn't change the idea, right? The idea still was the whole point was to put a good leaving group on its oxygen so it could be attacked. Right? I put the Br on its oxygen so it could be attacked. So let's just call this, we're just going to do a kind of a reaction review. Make sure I don't forget anything. Simplest things first, right? SN2, right? one step, two things, right? One step, no tertiary, and only sp3, right? And only sp3. Usually a small nucleophile, small reactive, usually with a negative charge nucleophile. All those kind of things. We talked about, obviously inversion of stereochemistry. Anything else for that one? So obviously no sp2 hybridized things, right? Only sp3, no tertiary, only primary, secondary carbons. SN2 prime. That's a little different. In these cases, let's say I have this, and I have CN. It's just easier to show the mechanism for this one. Right, I can't, right, the nitrile can't do an SN2 here, right? Because that carbon is tertiary. The bromine, right, that bromine is attached to a tertiary carbon. It's sp3 hybridized, but it's tertiary. You can't do SN2s on tertiary carbons. But you could have this attack the pi bond, have the pi bond shift over and kick the bromine out. That's SN2 prime. Usually the double bond moves, right? You see the double bond move. That's kind of the dead giveaway. Because now the pi bond's over here, and the nitrile piece is on the other end, and you made Br minus. So SN2 prime is just a way to essentially do a substitution without having to attack the carbon directly. Right? So you don't attack that carbon directly. That's the key. The carbon with the leaving group doesn't get attacked directly. It gets attacked in a different place, the prime position. Right? A couple bonds away. It's almost like a beta addition into it. Okay, so now let's go to E2, which we should know more about. E2. Right? It's obviously, again, one step. We're not so worried about the tertiary. Actually, it's better for tertiary, right? So usually the more substitute the alkene, the better, right? So more substituted, usually it's the better. But it can it can work with primary, secondary, and tertiary. Alkyl halides, it works with all of them. The biggest thing with E2 is this conformational thing, right? Just like SN2 gets this inversion, E2 needs to be in a particular conformation, and that is anti-periplanar. Okay. Got to be anti-periplanar. So we saw a lot of ring flips, right? We talked about ring flips. You got to get things axial in rings, right? You got to get the H in the leaving group axial. The leaving group, and then H. That's where you find out where the pi bond's at, but you gotta get them axial. That's the key. Gotta be anti-periplanar. That's the key for E2. Right? Usually bulky base, those kind of stuff. Right? Bigger base is good. Now, E1CB. That is 2 steps. Right? And it's unimolecular. The rate depends only on the intermediate. Whereas E2 and SN2 prime, right, all of these, right, depend on 2 things. It's a bimolecular reaction. There's a nucleophile and an electrophile. Right? There's a base and a leaving group, right? Alkyl halide. There's 2 things. E1CB only relies on 1 thing in the rate determining step. So the way E1CB works, let's say you have this. Now you could just do an E2, right? I could have, a big bulky base, and I could just do an E2 elimination, make it anti-periplanar. But let's say this was in a ring where I can't get this H. Well, let me just make it into a ring. And I'm not going to worry about the stereochemistry, but just humor me. This H and this Br can never be, they're not trans. They're just not trans, and they'll never be trans. but I still can do an elimination. It's just through a different mechanism. So let's say, let's just draw it. Let me just make this happen. So that bromine's, that H is up, this bromine's up, and now there's a methyl group back here going away, right?
There are two H's there, so one would be.
Well, I'm drawing a methyl in now, so, right? So there's an H and then there's a methyl, right? So I'm drawing that in now. So this H and this Br can never, ever, ever, ever be trans, right? It just can't happen. They're always going to be cis. And let's just say I'm blocking these two spots too. I'm putting two methyls down there. So now nothing can be anti-periplanar to that bromine, right, in this ring. Nothing can be anti-periplanar to it. The bromine can be axial, but this H then will be equatorial, right? Nothing will be anti-periplanar to it. But let's say I do get the elimination to happen. How is that possible? So this is how it's possible. Basically, the bulky base deprotonates, and instead of doing an elimination right away, that negative charge just goes to that carbon in the alpha position. So it's actually this intermediate, right? This intermediate. So elimination, E1CB stands for elimination unimolecular conjugate base. So this is the conjugate base, right? So essentially you form this conjugate base, right? And then what it can do, it can finally just do this elimination and kick it down. But because you form that negative charge there, you don't need to worry about this, basically the anti-periplanar stuff like you do in E2. So you can still get the same kind of product you do from E2, but it has to be from a different mechanism because you know it cannot be anti-periplanar. So if it can't be anti-periplanar and you still get something like this, you had to realize and recognize it had to go through a different mechanism. That's the key. All right, so now let's talk through the other kind of sets of mechanisms we learned. We already did metal halogen exchange. We talked about that. Now let's talk about the nucleophilic aromatic substitution, or essentially addition, elimination. So what do you need for nucleophilic aromatic substitution? You usually need an electron pore ring, right? So a delta plus ring. You usually need probably a pretty good nucleophile. Obviously a good leaving group. So the hard part is like a lot of these mechanisms are hard to distinguish between each other. That's the whole point. And some of these questions I showed you guys, it's not a matter of getting it right. It's just explaining it logically, what is possible, right? So for this one, right, some dead giveaways, right? If you see electron withdrawing groups on the ring, right? The ketone's electron withdrawing, right? So if I put an iodine on here, right, it makes sense that whatever my nucleophile is, say it's this amine, right, that maybe it's not even charged like we did in lab. Like we did this in lab, and our amines that we did weren't even charged. They still could do this, right? They do an addition, right, because we can't do SN2, right? We can't do an SN2, but we can do an addition. Would there be a negative charge there? I and H, right? Plus charge. We can do an addition and then have these electrons come down and kick out the I minus for the elimination.
Why would it attack there, both of those?
So that carbon's still delta plus because that's where the iodine's at.
Even though you have withdrawing, so you're...
So it's even better, right? So this is pulling away electron density. That makes this carbon even more delta plus, right? It's getting pulled from a couple of different directions, right? And I could draw a resonance structure where I bring these electrons here to here, in resonance structure into that electron withdrawing group even, right? You see how I could do that? I could draw, right, I put the negative charge here, but I could do some resonance structures where I move these electrons around the ring and they actually go up into the ketone. Right, if I do some resonance structures, I could have something like this.
I thought it was drawing groups from meta.
You're thinking about electrophilic aromatic substitution. This is nucleophilic aromatic substitution. In this case, right, remember, the nucleophiles, the ring is actually the electrophile. In electrophilic aromatic substitution, the ring is the nucleophile. So in this case, this is getting attacked. So it's not about orthopara-directors. It has nothing to do with orthometa or para-directors. This has nothing to do with that. Completely different. Right? This nucleophile attacks that carbon because it's delta plus, because that's where the leaving group's at. But it can do SN2, so it adds in, electrons go up, and we have resonance structures because there's electrons drawing groups, so that stabilizes the negative charge in the ring. And there's a resonance structure here. So again, we're not worried, no orthometa para-directors. We add in, we can't do SN2, we put the negative charge up here. Electrons drawing groups can be stabilized by resonance. The negative charge comes down, kicks out what we don't want on the ring at the end. Right? And then at the final step, the I minus just takes the H, right? And we get our final product. Now, nucleophilic aromatic substitution is likely with, right, again, delta plus rings, right? We form one product, right? Where the leaving group's at, where the leaving group at, that carbon gets replaced by wherever the nucleophile is. The nucleophiles don't need to be that great, right? Notice how this nucleophile wasn't even, right, negatively charged. Right? Some of these are going to require the nucleophile to actually be really, really strong, and this one doesn't.
For elimination addition, those form two products.
Right. So this one only forms one product, right? Where this leaving group is at is where the nucleophile ends up. One product. Okay. Good. Now, a different type. Right, so that would be elimination addition, which is really the way we form. Well, one of the ways we form benzene.
But you can't call this is not a nucleophilic aromatic.
No, nucleophilic aromatic substitution was addition elimination. So you add in, break a pi bond, and then you'll do an elimination and recreate a pi bond. This one is an elimination addition, so we make a pi bond first and add something into it. So in this case, the keys here are, right, it's not so much, you can have a delta plus ring, actually. I take that back, right? So we could have the same exact situation as before, right? The same as the nucleophilic aromatic substitution. The only thing we're going to change here is our nucleophile, right? So it's still a delta plus ring, but for an elimination addition, we want a really strong base, right? We want something really strong. So instead of a nitrogen without a charge, we're going to have an N minus, right? Which is much more reactive and much more basic, right? So what it can do, right, is this elimination. Now, this is not to say nucleophilic aromatic substitution couldn't happen here too. It probably could. Right? But since it's a really strong base, maybe we think it's less likely, but it still could happen. But we're going to know it does or doesn't happen by the number of products we form. The tricky part is going to be when we have symmetry in the ring, and I'll show an example of that quick, of where benzene mechanism, this mechanism will still only give us one product. But let's look at this first. So we did an elimination. So we form that benzene. We have I minus. And usually we have more. I will be sure to tell you how many equivalences of things we have floating around, but usually we have more than we think. That's always one of the most frustrating things, was trying to figure out how many equivalences of things are supposed to be. I'll let you know. I'll do my best. But now we have a benzene. The benzenes are special because, right, they're good electrophiles, but this carbon and this carbon are both equally electrophilic. So we're going to form two products because of that. Right, we can form a product there. and we can form a product there. I'm just going to draw one. We're going to do the red or the blue. Let's do the red. So let's do the red. All right, so as the red adds, you also had to, right, you did elimination, now you got to do the addition, so you got to break a pi bond. So as it attacks, you bring that pi bond up. So there's now a negative charge here. The nitrogen added. Right? So now the negative charge, right, that benzene ring, this negative charge, of course, is not stabilized by resonance. It's perpendicular to the pi cloud, so it's not very happy. So it's going to take the H off one of the original things, and that gets us to our one of the possible products. Right? So if I just showed you this, right, this product is the same as the last one, right? The nucleophilic aromatic substitution. It's the same product. Right? Came from a completely different mechanism though. Well, same type of product, not necessarily exactly the same. But we're also here going to make this product. Right? Because remember the benzene you can attack two different ways. Two different carbons are electrophilic. So with the elimination addition benzene, usually you make two products, but not always. Right? There's a problem in that problem set I gave you guys where there's some symmetry, and also some in the book that are harder. So let's look at one where there's symmetry involved. It's going to be harder to predict. Let's see if I put, I won't do the O's. If I do the BRs. Plus right, so in this case, how many benzene products would you make, right? So you always make two. But now in this case, take a couple seconds to see how many products you'd make for this. Okay, so for this one, this is a little different. It's most likely a benzene, right? For a lot of reasons, right? Strong base, but it could also be a nucleophilic aromatic substitution, perhaps too. Right? Bromines are electron withdrawing. But let's look at the benzene mechanism here, because usually the easy dead giveaway is always like, oh, the benzene forms two products, right? The elimination addition mechanism forms two products. But if there's some symmetry in the molecule, that kind of goes out the window, doesn't work. Let's see that here. So if you draw the H in, doesn't matter which bromine we decide to kick out, but we go with this one. So we form the benzene, but what you'll see is, in this case, right, these two carbons normally are different, right? But in this case, they're not any different. They're the same carbon, same type of carbon. So it doesn't matter, right? Even though it's the elimination addition mechanism, I'm only going to form one product, right? So if I attack here, I would get the same product as if I attacked at that carbon too. Do you see that? Yeah, making sense? Let me just take the last hydrogen. Right, so in this case, we actually only form one product with the elimination addition mechanism. Right, there's two carbons that can be attacked, but we can still only form one product. So this would be even harder to distinguish between nucleophilic aromatic substitution and the elimination addition. But you could argue either way, right? You could say, well, still, this is still a strong base. That's more likely for elimination addition. Right? It's going to act like a base first before it does act like a nucleophile.
Could you
So-
also say like there's one H there compared to like all those bromines, so you could say like it's going to be
So more likely to do nucleophilic aromatic substitution then. You can say that too. right? So it's really electron poor, so it's really more likely to do electrophilic aromatic, or more likely to do nucleophilic aromatic substitution. You can say that too. Usually I'd give you the product, but in this case I'd give you the product, and you could argue either way, and either way would be right. It'd be fine. So the final thing we kind of haven't got mechanism is the old SRN1. All right. So this one is obviously a radical. Let's show it. Right, so it doesn't really, for the radical, electrons drawing on the ring isn't really that big of a deal. We know it's not going to be a super strong base, right? Strong bases are for elimination additions. Electron drawing rings are a lot more nucleophilic aromatic substitution. So SRN1, usually the dead giveaway is you see, right, wavelength or light or heat or something. The other thing you can look for is the type of nucleophile. So it's something that's not super nucleophilic. Something that's kind of a fat guy, like maybe a sulfur, right? Even though sulfur has a negative charge, sulfur's a little bigger. It's not holding those electrons as tight. It's more willing to give up maybe one electron. The other example I showed you guys quite a bit was things that can do resonance, right? So like an enolate. So if you can do resonance, that usually is a pretty good radical source, right? So actually the nucleophiles have to be kind of stable for these resonance SRN1s, right? Because they're going to donate one electron. So the kind of the dead giveaway, I mean, this is a dead giveaway. And then the types of nucleophiles are not really strong nucleophiles, right? They're either fat elements or they're resonance stabilized nucleophiles. They're more likely to give up one electron at a time. Right. So, one electron in. This is really the extent I wouldn't expect you to know, because even I have trouble saying this sometimes. All right, so you get that 3 electrons. What? The Todd. Very good. The triangle of dots, the Todd. The therefore sign, or in this case, the 2-centered 3-electron deal. Whatever. Philosophy, chemistry, uniting. I might as well just leave, take the 2 electrons, and go. Left with a dot here. At the end of the day, the final step then,
How is that not propagation?
it's kind of a propagation step, I guess. These 2 guys come together. Single-headed arrows. Be careful, right? Single-headed arrows always. At least in this case. Always in this case. All right, so the key is going to be that light, the type of nucleophile. All right, that's going to be the kind of key for these. The other big ones you'll see for this, you'll see for this, these SRN1s, and the dead giveaway is an sp3 hybridized carbon that does a substitution, and that sp3 hybridized carbon is tertiary. Right? You cannot do tertiary SN2s. For the love of God, it just doesn't happen. Right? You cannot do SN2s on tertiary carbon. Right? For the love of all that is holy. Right? And a lot of times you want to do SN1, right? Everybody wants to do an SN1, but we're in strong base. We cannot form carbocations. We're in strong base. We are not forming carbocations. We are in strong base. Negative. They're in strong negative charges. So if I add in this, and I tell you the product is that, and I minus, right? I can't do an SN2 on this carbon. That's a tertiary alkyl halide. I can't do SN1 because, right, I have negative charges floating around. It just doesn't work. Right? So if it can't be SN2 and I'm in basic conditions, negative charges, it has to be SRN1. That's the only thing that's possible. The only other condition that can happen, something that can happen here, is if there was a pi bond off somewhere, but that would form a completely different product. Right? So let's look at that. Right? Let's say.
Did it have a pi bond on that? Could you technically get a mixture of products?
Yeah. So let's say I threw a pi bond on there. We actually would get a mixture of products. We'd get the SRN1 product, and we'd also get, see if I can do this. We'd also get, boom, 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 boom. Let me number my carbons because that's going to help here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is the SRN1 product. This would be the, if I had 5, 4, 3, 2, 1. This one would be the SN2 prime product. Right, the SN2 prime product. So that would be possible to get a mixture of products here. But for sure, you're not doing an SN2 on that tertiary carbocation. Right, and you should be able to see it pretty evident. Oops, I forgot something for the SN2 prime. Right, the other key feature of the SN2 prime is what? The double bond moves. So the new double bond is going to be between 2 and 3, actually. Right, the new double bond between 2 and 3. Right, as it attacked in and kicked out that I minus. Good. Mechanisms, we've seen both of them already, so that shouldn't be a problem at this point. Right, but again, recognizing the products, rationalizing the mechanism out through.